Good morning, all. In this video, we are going to look at the solved examples for chapter 4, transient analysis. Let's go here and look at example 1. Example 1 has an inductor, and you have a current source of 20 amps. Now, we are told that the switch in the circuit has been closed for a very long time before it is opened at time t equal to 0. Well, the beginning of the analysis, we want to set up our problem correctly. And to set up the problem correctly, we would draw or redraw the circuit. Redraw the circuit for time t less than 0 and time t greater than 0. So let's go ahead and do that. So the first step, as I was saying, draw the circuit for time t less than 0. And the key words here are a very long time. So a long time means sufficient time has elapsed for the circuit to reach a steady state. And at steady state, the inductor is fully charged and it is behaving like a short circuit. So if that's the case, then everything else in the circuit is effectively removed because it is in parallel with that short circuit. Okay, and so for t less than 0, all we have is a current source, and the current is flowing through that inductor. So when the switch has been closed for a very long time, the current through the inductor is 20 amps. This would be the current right before the switch is flipped, the IL at 0 minus. Now, when the switch is flipped at t equal to 0, the circuit changes. The source and the 0.1 ohm resistor is disconnected, and all we are left with in the circuit are the 3 resistors to the right. Now, if we examine the circuit, we see that there is no source in the circuit. So, if there is no source, it is a natural response problem, meaning it is discharging. Now, we see here that there are 3 resistors in the circuit. So the inductor is discharging through all those 3 resistors. However, it is possible to reduce that resistive network to one single resistance. And we can redraw the circuit like this, where we have one single inductor and one single resistor, which is Req, representing the total equivalent resistance as seen by the inductor L. Meaning you have to calculate the total Req between these terminals here. And once we do that, we can see that the 40 and 10 ohm resistor are in parallel, and then that would be in series with the 2 ohm resistor. So 40 and 10 in parallel is 40 times 10 divided by 40 plus 10, 400 over 50. 8 plus 2 gives me 10 ohms. Once I have Req, calculate tau, and tau is L over R. L over R gives me a tau time constant value of 0.2 seconds. 0.2 seconds. I can also write IL of 0 plus is equal to IL 0 minus, which is equal to 20 amps, meaning the inductor, when it begins discharging the energy, has a value of 20 amps. Remember, current through an inductor cannot change instantaneously, and that is the principle we use to determine the initial voltage for that inductor. Sorry, initial current for that inductor. And so from here, we can write I0, the initial value at the beginning of discharge, is equal to 20 amps. And because it is a discharging problem, the final value IF will always be equal to 0. So We take the general equation and we plug in our values. In the general equation, we have x of t. In this case, we are solving for the current of the inductor. So x of t, x of course is IL. And so we have the expression IL of t is equal to IF plus I0 minus IF e raised to minus t over tau. Plug in the values. IF is 0, of course. It's a natural response problem, discharging. And I0, the initial value is 20 amps. And then tau is 0.2 seconds. Plug in all the values, reduce it, and you have your final answer as IL of t is 20 times e raised to minus 5t amps. Again, overall function is still describing the current. So the unit is always amps. And this equation is valid for all time values greater than or equal to 0. And that is the procedure to solve for the natural response of an inductor. Next, let's take a look at example 2. Similar example. This time, we now have a capacitor and follow the same process as before. And in this process, we can see that the capacitor was connected to the source for a very long time. So switch has been in position X for a very long time, which is right here. So if we redraw the circuit for time t less than 0, we obtain the voltage source connected to the capacitor. Sufficient time has elapsed for the capacitor to reach steady state, and so capacitor is fully charged to a value of 100 volts. So from this, we can write that initial value V0 is 100 volts. Now at time t equal to 0, the switch is flipped to position Y. When it's flipped to position Y, the circuit changes and we now have 3 resistors connected to that capacitor. Similar to the previous example 1. There is no source in the circuit, so it is a natural response problem, discharging problem. And we can reduce the 3 resistors to a single REQ as seen by the capacitor between those terminals. REQ is the 240 kilo ohm resistor in parallel with the 60K, and which is then in series with the 32 kilo ohm resistor. And that gives us a value of 80 kilo ohms. From there, we can calculate tau. Tau is simply the product of the resistor and the capacitor, R times C. And so tau now becomes, or now we obtain tau as 0.04 seconds, 0.04 seconds. Initial value of the capacitor at the beginning of discharge is 100 volts. So V0 is 100. Vf is going to be 0 volts. Use the general solution. General solution, the variable of interest is x of t. Because it's a capacitor, we're solving for voltage. And so x is Vc. And we write the expression, Vc is equal to Vf plus V0 minus Vf e raised to minus t over tau. Plug in all the values and reduce the expression to its final form, where Vc of t is given by 100 times e raised to minus 25t. Overall units is describing voltage, so the units have to be volts. And this expression is valid for all time values greater than or equal to 0. Take a pause, review both examples, and let me know if you have any questions. Okay, so move on to example 3, last and final one. And here we have a capacitor of 10 microfarads. There is a current source of 10 milliamps and a switch which is flipped open at time t equal to 0. So let's begin by drawing the circuit for time t less than 0. So t less than 0, let's assume that the switch was closed. And if the switch was closed, the circuit looks like this, meaning the current source is short-circuited and all of the current is flowing through there. Now, in real life, of course, we are never going to short out a source. This is just to show that all of the current from the current source is not, nothing is going to that capacitor or the resistor for that matter. Meaning, for a very long time in the past, all of the energy in the capacitor was already discharged through that resistor. So discharged previously. Okay, discharged previously. And so we can say initial voltage across the capacitor is 0, hence V0 is equal to 0 volts. Okay, there is no mention of any other charge present on that capacitor. Now, t greater than 0, the switch flips open. When the switch flips open, the circuit becomes like this. The current source now has passage only through the resistor and the capacitor. If we examine the circuit, we have a source present, and so this is a step response problem. A step response. Now there are two ways to determine the voltage across that capacitor at steady state, right? So at t is equal to 0, the capacitor will begin charging, right? And the switch flips. Initial value is 0. We need to determine what the final value is. Final value can be determined by applying source transformation, right? Source transformation, we can take the current source, which is in parallel with the resistor, and convert it into a voltage source, which is in series with that same resistor. Think back to chapter 2, source transformation. So the resistor remains the same. The voltage is now given by Ohm's law, so 10 milliamps times 2 kilo ohms, which is 20 volts. Capacitor starts charging. Time constant of the capacitor is tau is R times C, 0.02 seconds. And the final value of the voltage can be determined as VF is equal to the source voltage, 20 volts. An alternative way of determining this voltage is to look at the capacitor at steady state. So at steady state, what happens? Capacitor reaches full charge and it behaves like an open circuit. So open circuit right here. So at steady state, all of the current from the current source is going to go down this path, meaning through the resistor. And if all of the current is going through the resistor, what is the voltage drop across the resistance? Well, given by Ohm's law, 10 milliamps times 2 kilo ohms, 20 volts. So if VR is 20 volts, VR and VC have to be the same because they're connected in parallel. And so my final value of the voltage in that capacitor at steady state is also 20 volts. I'll suggest you pause here and consider both of these circuits and both of these methods. Think over it and let me know if you have any questions. After that, simply take our general solution. And remember, general solution works for both charging as well as discharging. Here, my V0 was 0, VF is 20, X of t variable, X is the capacitor voltage VC, plug in all my known values, and I obtain my final equation as VC of t is 20 minus 20 times e raised to minus 50t volts, which is valid for all values of time greater than or equal to 0. Right, so those are the 3 example problems. Now in the homework, there are some problems relating to energy. There's also a question where it asks you to determine the time required for the voltage to reach half, or the energy to reach half. In those homework problems, what you would do is you would use the equation for the energy as half CV squared, and half energy means 50% of the energy. You would calculate the voltage required, VC, at 0.5 times the energy. And then you take that VC and solve for time. So this is one of the homework problems. I can't remember which one it is, but if you run into issues, please send me an email, get in touch with me. I'd be more than happy to help you out. Okay, so this is the end of chapter 4. From here on out, we will look at AC analysis, chapter 5.